Hello friends, welcome you all to the 47th lecture on function analysis and its applications. In this lecture, we will discuss the partially ordered set and positive operators. These are the contents of today's lecture: partially ordered set and positive operators. Partially ordered set. A partial order less or equal on a non-empty set X is a relation which satisfies the following conditions. First, X less or equal to X for all X belonging to X, that is reflexive. Second, X less or equal to Y and Y less or equal to X. This implies that X is equal to Y for all xy belonging to X. This condition is known as antisymmetric. And third, X less or equal to Y and Y less or equal to Z. This implies that X less or equal to Z for all x, y, z belonging to X. This condition is known as transitive. The pair X and less or equal is called a partially ordered set. Next definition. Let S be the set of all self-adjoint operators on a Hilbert space H. We define a relation less or equal on S as follows. If A1, A2 belonging to S, then we write A1 less or equal to A2. If inner product of A1x and x less or equal to the inner product of A2x and x for all x belonging to H. In the following theorem, we shall prove the relation less or equal defined on the set of all self-adjoint operators is partial order relation. Theorem. The real Banach space of all self-adjoint operators on a Hilbert space H is a partially ordered set whose linear structure and order structure are related by the following properties. First property, if A1 less or equal to A2, then A1 plus A less or equal to A2 plus A for every A. And second, if A1 less or equal to A2 and alpha greater or equal to 0, then alpha A1 less or equal to alpha A2. Let us prove it. Let S be the set of all self-adjoint operators on H. We define the relation less or equal on S as follows. If A1 and A2 belonging to S, we write A1 less or equal to A2 if inner product of A1x and x less or equal to inner product of A2x and x for all x belonging to H. We shall show that less or equal is partial order relation on S. That is, we have to prove all three conditions, that is reflexive, antisymmetric and transitive, are less or equal. Okay. So first property, let A belonging to S, then inner product of AX and X, that is inner product of AX and X for all X belonging to H. Therefore, we have relation inner product of AX and X less or equal to AX for all X belonging to H. Hence, by the definition, A less or equal to A, therefore the relation less or equal on S is reflexive. Second, less or equal is antisymmetric. So, let A1 less or equal to A2 and A2 less or equal to A1. Then to show that A1 is equal to A2. Okay. So we have, as per the definition, A1 less or equal to A2. This implies that inner product of A1x x less or equal to inner product of A2x x. Also, A2 less or equal to A1. This implies that inner product of A2x and x less or equal to inner product of A1x and x. From these we get inner product of A1x x equal to inner product of A2x x. This implies that this side inner product of A2x and x, that is, we can write inner product of A1x minus A2x x equal to 0 by the additive property of inner product. Okay. So this can be written as A1 minus A2x, that is, this equation can be written as inner product of A1 minus A2x x equal to 0 for all x belonging to h. So we know that inner product of T x x is equal to 0. This implies that T is 0 operator. So here inner product of A1 minus A2x x equal to 0, that is, A1 minus A2 is 0 operator, that is, A1 is equal to A2. Therefore, the relation less or equal is antisymmetric. Third, the relation less or equal is transitive. Let A1 less or equal to A2 and A2 less or equal to A3. Then inner product of A1x less or equal to inner product of A2x x. Similarly, this as inner product of A2x and x less or equal to inner product of A3x x. From these we get inner product of A1x x less or equal to inner product of A3x x, because here inner product of A1x x less or equal to inner product of A2x x and inner product of A2x x less or equal to inner product of A3x x. So putting the value of inner product of A2x x in this, we get this one. Therefore, by definition, A1 less or equal to A3, and so the relation is transitive. Hence, less or equal is partial order relation on S. Now we shall prove the next part of the theorem. We have A1 less or equal to A2. This implies that inner product of A1x and x less or equal to inner product of A2x and x. Adding in this inequality inner product of AXX both sides. So as per the definition of inner product, this part can be written as inner product of A1 plus AX and x less or equal to, this is also can be written as inner product of A2 plus AX x. Hence, comparing this, so this one less or equal to this, that is A1 plus AX less or equal to A2 plus AX, that is A1 plus A less or equal to A2 plus A by the definition of less or equal. Second part, we have A1 less or equal to A2. This implies that inner product of A1x x less or equal to inner product of A2x x. Let alpha is non-negative, so we can multiply both sides of this inequality, that is there is no change, so we can multiply. So this implies that alpha into inner product of A1x and x less or equal to alpha into inner product of A2x and x. So as per the linearity property of inner product, this can be written as inner product of alpha A1x and x less or equal to inner product of alpha into A2x x. This implies the inner product of alpha A1 x x less or equal to inner product of alpha A2 x x. Okay. So as per the definition of less or equal, this is alpha A1 less or equal to alpha A2. Hence proved. Positive operators. Definition: a self-adjoint operator T on a Hilbert space H is said to be positive if T greater or equal to O. That is zero operator. Okay. That is if inner product of T x x greater or equal to 0 for all x belonging to H. From this definition, we have the following properties. First, the identity operator I and the zero operator O are positive operators. Okay. Explanation. We know that the identity operator I and zero operator O are self-adjoint. Further, inner product of Ix and x, that is inner product of xx, and inner product of xx, that is norm x square. Norm x always greater or equal to 0. Hence, inner product of Ixx greater or equal to 0 as per the definition. If inner product of Txx greater or equal to 0, that is T greater or equal to 0 operator. Okay. So I, that is identity operator, is positive operator. Similarly, 0 operator, it is also self-adjoint. So inner product of Ox, O that is 0 operator, inner product of Oxx, that is inner product of 0x. Inner product of 0x, that is 0. So this is 0, it means T is 0 operator. Hence I and O is positive operators. Second property, for an arbitrary T on H, then TT star and T star T are positive operators. T star, that is the adjoint of T. First we note that TT star and T star T are self-adjoint. Okay? Because inner product of Txx greater or equal to 0, that is T greater or equal to 0 operator, where T is self-adjoint. Okay? So we have to prove TT star and T star T are positive operator. So first we have to prove TT star and T star T are self-adjoint. So let us prove it. Star of TT star equal to star of T star into T star, because we know that T1 T2 star equal to T2 star T1 star. Okay. So as per this definition, we can write this as star of T star into T star. That is star of T star, that is T double star. And also we know that T star is equal to T. So this is T star. Okay. So here star of TT star is equal to TT star. So we can say that TT star is self-adjoint. Similarly, T star T also self-adjoint, proof as similar. That is star of T star T. Again, applying this property, we can write this is T star into star of T star. That is T star into T double star, and T double star is T, that is T star T. Hence, star of T star T is equal to T star T. So, T star T is self-adjoint operator. Now, prove they are positive. Inner product of Tt star x and x equal to, as per the definition of adjoint operator, that is inner product of T x y equal to inner product of x and T star y. Okay. So, as per this definition, this can be written as inner product of T star x and T star x. That is, inner product of Tt star x can be written as inner product of T star x and T star x by this definition. Here both points are same. So, we know that inner product of xx is equal to norm x square. So, this is norm of T star x square. Norm always non-negative, that is, this is greater or equal to 0. Okay. So, here this proves that Tt star is positive operator. Similarly, T star T is positive. So, we can prove as this, that is inner product of T star Tx and x can be written as by this definition, that is inner product of Tx and star of T star x, that is T double star x, and T double star x, that is T. So, this can be written as inner product of Tx and Tx, that is norm of Tx square. Norm always greater or equal to 0, that is norm Tx square greater or equal to 0. Hence, again we have proved T star T is positive operator. Therefore, Tt star and T star T are positive operators. Theorem: if T is positive operator on a Hilbert space H, then I plus T is non-singular, where I is the identity operator. In order to show that I plus T is non-singular, we are to show that I plus T is 1 1 and onto as mapping of H into itself. So, we prove first I plus T is 1 1. We shall first show that I plus Tx is equal to 0. This implies that x is equal to 0. So, let us prove it. We have I plus Tx equal to 0 vector. This implies that Ix plus Tx equal to 0, that is x plus Tx is equal to 0. This implies that Tx is equal to minus x. Okay. So, we can write this as an inner product, that is, this implies that inner product of Txx equal to inner product of minus xx. Okay. So, as per the definition of inner product of alpha x y equal to alpha inner product of x, y. Okay. So here minus outside, that is, this can be written as equal to minus x, that is inner product of xx is norm x square. So inner product of txx is equal to minus norm x square. Okay. So here t is positive operator, then inner product of txx greater or equal to 0. Okay. Then minus norm of x square greater or equal to 0 as per inner product of txx greater or equal to 0. Here minus sign, that is, this can be written as norm x square less or equal to 0. Okay. Norm x square less or equal to 0, this implies that norm x square equal to 0 because norm always non-negative. Okay. So only one possibility, this one should be 0. So norm x square is equal to 0, this implies that x is equal to 0. Okay. So we prove here x is equal to 0 vector. Thus I plus tx is equal to 0, this implies that x is equal to 0. Now I plus tx is equal to I plus ty. This implies that I plus t minus I plus ty equal to 0. That is this one left side. So as per the definition of linearity property, this can be written as I plus t x minus y equal to 0. Okay. So here we prove I plus tx is equal to 0. This implies that x is equal to 0. So here I plus t x minus y is equal to 0. That is x minus y is equal to 0. That is x is equal to y. Hence I plus t is 1, 1. Now we shall show that I plus t is onto, let m be the range of I plus t. Then I plus t will be onto if we show that m is equal to h. First we shall show that m is closed. For any vector x in h, we have norm I plus t x square. That is, this can be written as norm of x plus tx square. And this can be written as inner product of x plus tx and x plus tx. So as per the additive property of inner product, this can be written as inner product of x plus inner product of x tx plus inner product of tx plus inner product of tx and tx. Inner product of xx, that is norm of x square, and if we change the point of this inner product, that is conjugate complex of the inner product of tx and x, plus this is as it is and this one as norm tx square. So this expression can be written as norm of x square plus 2 inner product of txx plus norm tx square. Okay. Why? Because here t is positive operator. Okay. That is, t is self-adjoint. We know that inner product of txx bar is equal to inner product of Txx. Okay. So here positive, that is real. Okay. So inner product of Txx bar is inner product of Txx. So this expression can be written as norm x square plus 2 into inner product of Txx plus norm Tx square. Okay. So this norm I plus Tx square greater or equal to norm x square, because T is positive, that is inner product of Tx greater or equal to 0. So this is greater or equal to 0. It means norm of I plus Tx square greater or equal to norm x square. Thus norm x less or equal to norm of I plus Tx, or all x belonging to x. Equation 1. Now let I plus Txn be a Cauchy sequence in M. So for any two positive integers mn, we have norm of I plus Txm minus I plus Txn converges to 0 as mn tend to infinity. Okay. So now norm of I plus Txm minus I plus Txn equal to norm I plus Txm minus xn. Okay, we can write as per the property of linearity. So using 1 and 3, okay, so it can be written as norm of xm minus xn less or equal to norm I plus Txm minus xn. As per this inequality, we can write this one as this. This implies that norm xm minus xn less or equal to I plus T xm minus xn, and here I plus T xm minus xn, that is I plus T xm minus I plus T xn. Okay. So here this one from 2 converges to 0. So norm xm minus xn converges to 0. This means that xn is a Cauchy sequence in H. But H is complete because this is a Hilbert space. Hilbert space is complete space. Therefore, the Cauchy sequence xn in H converges to a vector, say x in H. Now since I plus T is continuous mapping, so limit I plus T xn equal to I plus T limit xn, we can write as per the definition of limit, equal to I plus Tx, because xn converges to x, and this belongs to M. Thus the Cauchy sequence I plus T xn in M converges to a vector I plus Tx in M. In this way, we see that every Cauchy sequence in M is a convergent sequence in M, therefore M is complete. But every complete subspace of a complete space is closed, hence M is closed. Now we shall show that M is equal to H. Suppose M not equal to H, then M is a proper closed subspace of H. Therefore, there exists a non-zero vector x0 in H such that x0 is orthogonal to M. We have already proved in the previous lecture, if M is proper closed linear subspace of Hilbert space H, then there exists a non-zero vector x0 in H such that x0 perpendicular to M. So by this theorem, we have x0 is orthogonal to M. Since I plus t x0 belonging to M, therefore x0 perpendicular to M. Meaning of this is inner product of I plus t x0 and x0 is equal to 0. Okay, because I plus t x0 belonging to M. So this can be written as inner product of x0 plus t x0 and x0 equal to 0. As per the additive property of inner product, this can be written as inner product of x0 x0 plus inner product of t x0 x0 is equal to 0. This is norm x0 square plus inner product of t x0 x0 is equal to 0. That is minus norm x0 square equal to inner product of t x0 x0. Okay. So inner product of t x0 x0 greater or equal to 0 because t is positive operator. So norm x0 square greater or equal to 0. So as per the property of inequality, norm x0 square less or equal to 0. So norm always greater or equal to 0, then this should be 0. That is norm x0 square is equal to 0. This implies that x0 is equal to 0. But this contradicts the fact that x0 is non-zero vector. Hence, we must have M is equal to H, and so I plus T is onto. Corollary: if T is an arbitrary operator on H, then the operators I plus Tt star and I plus T star T are non-singular. Proof: for any arbitrary operator T on H, we know that Tt star and T star T are both positive operators. Hence, by the above theorem, both the operators I plus Tt star and I plus T star T are non-singular. Example: if T1 and T2 are positive operators on a Hilbert space H, then T1 plus T2 is also a positive operator. This is the example of positive operators. Since T1 and T2 are positive operators, therefore inner product of T1 x greater or equal to 0 because T1 and T2 are positive operator. Also here inner product of T2 x greater or equal to 0. Now inner product of T1 plus T2 x equal to inner product of T1 x plus inner product of T2 x. It can be written as, and as per equation 1, this is greater or equal to 0, this is also greater or equal to 0. Therefore inner product of T1 plus T2 x and x greater or equal to 0, hence T1 plus T2 is positive operator. In this lecture, we have discussed the partially ordered set and positive operators. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Narissi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.B. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.